Here, we'll talk about very interesting discoveries about pattern avoidance in graphs.
All right, thank you. So, I'm going to be talking about pattern avoidance. Since I think we've had a pattern avoidance talk here for a while, let's go over some basic definitions. So, here's the first definition. I have a word, W, which consists of letters, W1 through Wn. And so we call this a word, we call each of these letters, and letters are just numbers between 1 and some n. All right, and so we're going to say that this word contains the pattern P equals P1, P2 through Pk. So again, the P's are just numbers between, well, in this case, the P is going to be a permutation of the numbers 1 through K. And so W contains P if there exists some sequence L1 strictly less than L2 less than Lk, such that W Li is less than or equal to W Lj if and only if Pi is less than or equal to Pj. So here's the definition of containment, and otherwise W avoids P.
But P is a commutation.
Yes.
So why could be there?
Yes, so we could have just as easily said
Okay, no.
if Pi is strictly less than Pj. Alright, so otherwise we say that W avoids P. Let's look at an example. Alright, so for example, we have that 3, 2, 4, 2, 3, 1, 4, 1 contains 1, 2, 3 because I can find these three elements and they occur in the same order in this word as they do in 1, 2, 3. First, then the middle, then the smallest, middle, then largest. Alright, and conversely, 3, 3, 2, 4, 2, 1, 4, 1 avoids 1, 2, 3. So convince yourselves that is true. So, actually I can probably keep on working on this word. In general, we're going to be looking at words on the alphabet N through R, which is equal to 1, so R copies of 1, R copies of 2, R copies of N, R, and R. So in total, so in total, all of our words will contain the letter 1 once, the letter 2 1 or R times, and then so on. So all in all, we'll have R times N letters.
There's also dot between the 2 and N.
Did I forget a dot there? I forgot a dot there. Dot. Yes,
Yeah.
Matthew.
So just sorry, quick to go back to the original definition. Does 111 contain the pattern 1, 2, 3?
No. Do I mean? Does it? Is that true the way I wrote it?
Yeah,
I might mean.
Yeah. Okay.
That might be what I mean. Okay. All right. No, 111 does not contain 1, 2, 3. So, one question that you might ask is how many patterns, or how many words, and let's just say on N to the 1. So now we're looking at permutations of 1 through N. Avoid 1, 2, 3. we'll start. So today, we're going to actually do three things. The first thing we're going to do is we're going to answer this question, and then we're going to answer this in a way. This is has been answered for a long time. We're going to answer it through a specific strategy that Dr. Z created called enumeration schemes that will motivate the next step that we're going to do. So the next thing that we're going to ask is we're going to ask how many on and to the R now. So now we're talking not about permutations, but about these more general words. Avoid 1, 2, 3, and 1k, k minus 1, all the way down to 2. And then the third thing that we'll talk about is how many on n to the r, avoid 1, 2, 3, 4, and 1k, k minus 1, down to 2. So this has been known for a while. This is known in the case when r equals 1, but no one has really studied it at all for r greater than 1. And this is not even, or previously was not known even in the case when r equals 1. For k bigger than 5. For k, 3, and 4, it was. All right. So let's start with the first question. How many avoid 1, 2, 3? So let's give them a name. A sub n is the number of permutations of 1 through n that avoid 1, 2, 3. And a I sub n is the number that also avoids, or I'll write it down. So avoid 1, 2, 3, and begin with I. And so what we're going to do is we're going to find a recurrence where we write a sub I in terms of other terms like that, in terms of a sub j's, and then you could solve that recurrence and find a general formula. And so the recurrence looks something like this. Well, let's think about a sub ij. So a sub ij is all the words that start with I and then have a j and avoid 1, 2, 3. So what happens if I is bigger than j? So we have some element I, and then we follow with some smaller element. Well, if I were ever to be part of a 1, 2, 3 pattern, I could use that 2, 3, add on j, and make another 1, 2, 3 pattern. So I will never uniquely cause a problem, and I can just sort of forget about it. And so this is going to be equal to a j n minus 1. Because I'm forgetting entirely about I. So another thing that could happen is I could be bigger than j, or sorry, less than j, but then j could be not the very largest letter. And so let's say that j falls somewhere in between I and n. Well then, I'm going to inevitably have a 1, 2, 3 pattern that's going to be I, j, and then whenever n shows up, eventually it'll show up. And when it does, it'll be a problem. So there's no way to avoid 1, 2, 3 if I start like this. And then my final option is if if j is equal to n. Well, if j is equal to n, then it's not going to cause any problems because it can't possibly be followed by something bigger. And so I can just ignore it, and I'm left with I. AI of n minus 1.
So the first one be I greater than or equal to j.
Yes.
The second one should be I strictly less than j.
Yeah.
That is... Yes. Well, okay, so really we're talking about permutations right now, so j and I can't be equal. So I'll just get rid of both of those equalities. All right. So if we use this, we get, so let's just make a recurrence. We have ai of n is equal to the sum of j less than or equal to I of aj n minus 1. So all of the terms except for j equal to I come from this first case, and then the term where j equals I comes from the second case. And this is a recurrence, and we're really happy with it. It's not a finite recurrence, so it's not giving us a rational generating function, but it gives us a generating function that we're happy with anyway, which is 1 minus the square root of 1 minus 4x divided by 2x. And this happens to be the generating function for the Catalan numbers. And so we found a way to count all of these permutations, or all these permutations of the void 1, 2, 3. So we've solved the first problem. Well, Dr. Z solved this first problem like many years ago, but we've done it again.
Is this the same proof, or is this a different proof than the classical proof for the Catalans here?
I don't know. Sorry.
No, this is the classical result. Yet another proof.
So this is a new proof of the old.
Also very, so probably 10 proofs.
Sure.
Maybe that's proof.
It's just nice to see a 10th.
All right, so let's move on to our second question. So now we're going to generalize this a little bit. We're going to allow, instead of insisting that R be 1, we're going to say, let's have any number that we want of copies of each of our letters. And we're also going to say that instead of just looking at 1, 2, and 3, let's say that we also have to avoid this other pattern, 1k, k minus 1, down to 2. So let's rewrite the same thing that we had. So let's again investigate what happens if we insist that our permutations start with I. And we'll try to write it again in terms of, or we'll try to write what happens next in terms of all the possible options. So let's look at some of the possible options. So first of all, I could be less than j. But if I is a lot less than j, we're going to run into trouble. If j is a lot less than, if j is too small, we're going to run into trouble. And the reason that we're going to run into trouble is that if I have some element j, that is, so if j, let me move over here, we'll fill that in later. If j is followed by more than k minus 1 elements. So if j is followed by at least k minus 1 elements, well then either they're all going to have to be in decreasing order, and so I'm going to have, greater than itself. So if it's followed by more than k minus 1 elements greater than itself, then either they're all going to be decreasing, and so we're going to end up with one of these patterns, or two of them will be increasing, we'll end up with this pattern. So j can certainly not be, j has to be at least n minus k minus 1. And so but if j is at least n minus, if j is at least that large, then I can't possibly have a pattern that looks like this because I simply don't have enough elements for it. So I'm either guaranteed to create a pattern like this, or I don't have to worry about it. So let me write down what I actually have in my notes, and that will make my life easier. So I'm going to have the sum from j equals n minus k minus 1 to I of aj of n minus 1 if I is less than or equal to n minus 2 and 0 otherwise. All right, so let's think for a second about why this is true. Well, this looks a lot like the recurrence I had over here. The only difference is that instead of letting j be as small as I wanted it to be, I now say that j can't be any smaller than n minus k minus 1. And the reason for that is that if j were any smaller than that, then it would inevitably create one of these two patterns. But as long as j is large enough, then there just aren't k-1 elements left to create this pattern with it. And so then we're okay. And sorry, I realized that I lied a little bit. This is
Oh yeah, I remember.
n to the 1.
So, could you repeat the definition of n to the r? Is it a permutation of a multiset?
It is a permutation of that multiset, yes. So it's just a string of length n times r, where 1 occurs r times, 2 occurs r times, n occurs r times.
Thank you.
Yeah. All right. So this also has a generating function, and this time the generating function is rational, and it is negative 2x minus 1 over x squared minus 3x plus 1. Okay. And now my notes say to go to n to the r. But in order to do this, we need one more, maybe I'll just define one last thing over here.
So, because the summation now is finite.
Right, so now my summation is finite, because now I only have I have no more than k-1 terms here. And so because this summation has become finite, whereas this summation over here was arbitrarily large, I now get a rational generating function. So here's my definition. A left to right minimum is a letter such that no previous letter is larger. So we have a left-right minimum. If we're building our word, and we get to a letter and we see that it's smaller than everything that came to the left of it, then it's left-right minimum. And I'm going to call these LTR-Ms, just so I don't have to write this over and over again.
So could it be equal?
Sorry?
The definition says no previous left is larger.
Yes.
So what if they are equal?
Then it is not a left-right minimum. It won't really matter. We could still call it a left-right minimum. Maybe we will call it a left-right minimum, actually, just so that way I don't have to change my definition. All right. So what we're going to do is, so earlier we essentially, I didn't write A. I wrote A with a subscript, but I could have written it as sort of a 2-parameter function. And because we're now going to have to expand A to have several parameters, that's what we're going to do instead of just putting them all in the subscripts. So I'm going to have this new quantity called AR of little a, B, and L. And what this is going to mean is it's going to be the number of words with R copies of 1 up through A, B copies of A plus 1, and A plus 1 plus I copies of everything else. A1, and Li copies of A plus 1 plus I, where Li's are the elements of this list L. So L is the list of L1 through LT. And so so now I've told you sort of what the alphabet that all of these words are on. So these are all the words on this alphabet that has the letters I've described. But I have some more conditions. I want them also to avoid 1, 2, 3, and 1, k minus 1 to 2, even when a plus 1 is pre-pending. So the way I want to think about these words is I want to think about building a word piece by piece by piece, and at some point I have this left-right minimum, and my current left-right minimum is a plus 1. And I want to say, given that I have this current left-right minimum of a plus 1, and I have this list of letters that I still have to add, how many ways are there to finish my word in such a way that I don't end up with one of my 2 forbidden patterns? So that's the way that I want to think about this function a, or this quantity a. And the way to enumerate this is to think about what all of the possible next letters are. So one possible next letter is I could have a new left-right minimum. And in fact, like Yukon brought up, I'm actually going to want this left-right minimum to be sort of strictly new. I want it to be strictly less than a plus 1. So possibilities for the next letter is 1, it could be a new left-right minimum. It could also be a new copy of my existing left-right minimum. But it can't be anything bigger than that. I can't have anything bigger than my existing left-right minimum unless it's the very largest element possible, because otherwise when I add that very largest element possible, I'm going to end up with a 1, 2, 3 pattern. So it could also be n. And those are my 3 options, so we'll have 3 terms in our set. And maybe I'll move over here for that. So I'm going to get that A of R, A, B, L is equal to the sum from I equals A plus T plus 1 minus K minus 2. So this piece, this A plus T plus 1, is the largest element that I have left to add. And I'm saying that I can't be more than K minus 2 less than that, or else I'm going to run into that problem earlier where I either had to have an all decreasing sequence that was too long, or I had to have a length 2 increasing sequence. So that's why I can't go lower than this. And I also can't go higher, or I can't go higher than A, because then I wouldn't be a new left to right min. And if this is the case, so if I do have a new left to right min, then the number of ways to finish that word after adding my new left to right min is AR. So I'm still thinking of R copies of each letter. Except now instead of having A new untouched letters, I only have I minus 1 new untouched letters. And
so your approach only works if you have 1, 2, 3 and 1 K camera. So this particular approach doesn't work if it's only counting 1, 2, 3 words?
Right. This particular approach won't work for just the 1, 2, but there are other ways that we have to count words that only avoid 1, 2, 3. So this one is specifically for 1, 2, 3 and 1K.
So it would be a finite state.
Sorry?
So it would be a finite state, I guess.
Right. I guess if it wasn't, if we didn't have both of these to avoid, we wouldn't have a finite state recurrence, we wouldn't get rational generating functions. All right. So we have I minus 1 sort of new, unused, untouched letters left. And then we have, so now B counts the number of copies of our current left to right min that we've used. And our new left to right min is I, and this was the first time we ever used it. So we have r minus 1 copies left. And then this list L is the list of all the letter counts of letters that are above our current left-right min. So all of our letters that are above I. And so the first few letters that are above I, we have r of them left. So these are all of the letters that are between our new left-right min and our old left-right min. So I have R, I have a bunch of R's, I have A minus I of these R's, and then I have all of the old elements, all of the old letter counts that were already above even my previous left-right min. So that's L1 through Ln. Alright. So this term takes into account all of the ways to add a new left-right min. But now we could also instead add a new copy of our old left-right min. So we could instead add a new copy of A plus 1. And so if we do that, then we have a much simpler term. We still have A unused elements because we've used an old element. The only difference is that now instead of having B copies of that old element, we only have B minus 1 left. And all of the elements greater than that we haven't touched. We still have those same counts. Alright, so that takes into account the case when we have a new copy of A plus 1. And then the last case is, well, what if we finally add N? And if we add N, well, A stays the same because I'm not touching, I'm touching an old element that was already in L. B stays the same because I don't have any, I still have all the copies of A plus 1 that I did before. But L changes, just in that its last element loses 1. And these are the three options. One of these three things has to happen. And these recurrences alright, so these recurrences let us find lots of generating functions.
Let's your computer find. Not you.
Right, so it lets my computer find lots of generating functions, and it's pretty quick to find them as well. So, for instance, I got generating functions for r equals 2 and k up to 8 on my computer in less than a minute. So it's pretty quick to do these, even for k relatively large. Again, this result, so these generating functions were already known for r equals 1, but I think this is a nice and pretty simple way to generate them. And maybe even simpler than what was known before. Alright, so is there anything else that I wanted to say about that? Right, so I do want to just say, so briefly, the theme of this talk is we find the finite amount of information that we need to keep track of, and then because there's only this finite amount of information that we need to keep track of, we get these finite recurrences. So here, the only thing that we needed to keep track of was what letters we had left to use, and what our current left-right min was. And that was all that we needed to know. But unfortunately, as we move into our last case, there's a lot more that we need to keep track of, and so things will become a bit more complicated. Alright, so our last case, again, is what if instead of doing 1, 2, 3, we do 1, 2, 3, 4, and 1k, k minus 1, down to 2. As it turns out, so 1, 2, 3 was pretty simple. 1, 2, 3, 4 is not so simple, but also not that bad. And 1, 2, 3, 4, 5, I suspect it's impossible to find finite recurrences. At least I have no reason to believe that it would be possible. possible. So anyways, let's do this case.